I'm really excited to introduce our panelists today. We have Andre, who is joining us from Adelaide, and he's the director of the Institute for Photonics and Advanced Sensing at the University of Adelaide. They have over 220 members that are using photonic sensing to make the world healthier, wealthier, and safer, which is really cool. He's also the chair of experimental physics at the university and runs a research group there around field of precision measurement, clocks, magnetometers. I was like, don't ask me to spell that. I haven't had a second cup of coffee. And spectroscopy. So we're going to dig into all of that and what that means and unpack it for you who are not physics nerds on the call today. So welcome, Andre. It's great to have you here. Andrew, thank you for joining us. You've got a great backdrop there, and coming in from the ARC Centre of Excellence for Engineered Quantum Systems, or EQUS, up at UQ there. And I've got to say, Jacaranda time when I was at the university always reminded me of exams. So good luck to anybody that is in the middle of exams.
It reminds me of exam marking, so.
A little bit more painful and challenging. So Andrew's the director of the Centre of EQUS, as I said. It's a 14-year long research effort. There's over 180 scientists building quantum machines to harness the quantum world for practical applications. And we're going to understand, hopefully today, get an insight of some of those practical applications and what we're seeing happen. We've got Sean joining us, who's the founder of Shoal. So the founder and the head of business development of systems engineering house Shoal, who developed technology-intensive complex systems. He's a practicing systems engineer with a particular expertise in aerospace modeling and simulation and conceptual design. So I don't know what you all did for breakfast this morning or before lunch today, but I certainly didn't do that. So Sean and I met a couple of weeks ago, and he's actually created and sold, I believe, a quantum startup, which we'll hopefully get to hear a little bit more about as well. And last but certainly not least, to bookend our panel today, we've got Jacqui, who's a senior lecturer at the University of Queensland. She's a quantum physicist in EQUS, and she's also an experimental quantum physicist, studying the properties of single photons for the development of new quantum alphabets and the nature of quantum causality, which I have no idea what that means. But it sounds really cool. And actually that brings us to the very first question of the day. What I want to do is, I've introduced you from the bios, I've got you. I'd love to go around the panel, and I'm going to come to you first, Jacqui, and then we'll come through. But maybe in 1 to 2 sentences, can you tell us what it is you really do if you're talking to my mum or dad who own a fruit shop, or somebody who has no idea what entanglement is or quantum? What is it you do? Why are you passionate about it?
Okay, so what is it I do? I play with light, the particles of light, in particular their shape. I actually brought a prop with me. So can you see that? Aren't they pretty? They look like macarons, right? Yeah. So I can shape light like that. And you can use that as an encoding for your messages. So the goal of my research is, how do you harness this really nice property of light so you can have, for example, secure quantum communications someday.
Cool. That definitely is not what it says here. It says here in your bio, but I actually understood that. Andre, tell us what you do.
2 sentences.
It's great. I love it. Andre, tell us a little bit about what you do and why you're passionate about it.
Well, I guess what I really try and do is precision measurement, as you introduced me. So, if you want to understand the universe around you, and, that doesn't just mean the stars, but also, what's around us. If you want to build a better industrial process or understand what's going inside the body in terms of whether, your body's actually running correctly, then you need to have new types of measurement, and measurement that, you can really believe the results. If you've got that, then essentially you can progress. The measurement gives you understanding, and then with that understanding you can start to control the system. And so since that's sort of at the heart of what science is all about, but actually that can give industry our edge as well. So that's really what motivates me, is like handing to people the tools that allow them to understand things in better ways.
Awesome. I love it. So far with quantum, we've got 2 people explained what they do, and they haven't used the word quantum, which is great. So Sean, no pressure, but over to you.
Thank you, Sally Ann. So our company, we spend most of our time looking at large, complex projects and situations, and doing the early stage design of those. We got involved in doing some, and I'm going to use the word, quantum computing research and development with Lockheed Martin from the US a few years ago, and we took a tack of looking at the applications for this, not how to build a quantum computer. We let others do the physics and the hard engineering on that. We're looking at really what are the applications for that. Is it finance? Is it medical science? Is it sociology, transportation, etc.? And so we built a company starting in 2014, which we sold to a US firm last year, which focused exclusively on quantum or applications for quantum computers.
I love it. Sean, we're going to come back to that in a minute because I think the application piece is something really critical, but I do want to come to Andrew. So Andrew, it's all on your shoulders. You can tell us what you do, but then I actually want you to unpack quantum in a digestible way. And maybe if there's any difference at all between quantum and quantum technology, can you just give us a little bit of an overview as well?
All right, let me flip that. I'll start with unpacking quantum. So quantum is the physics and the rules for the universe as it gets very small. It was discovered about 120 years ago. And all of the technology, if you've got a phone, solar cell on your roof, any piece of modern technology that you use uses one part of quantum physics. And technically we call that the wave-particle duality, but it's the physics that let us make semiconductors. Right now, we're living through a second kind of quantum revolution where we're taking all the other rules for the universe as it gets small, the things that Jacqui mentioned, entanglement, for example, and we're making new technologies and engineering new technologies using those rules, and it lets us do things we couldn't do before. So Andre mentioned, the breakthroughs that he's able to get in sensors. Sean mentioned computers, but it's also everything from medical imaging through to timekeeping. If you know when you are, you know where you are in the world, through to looking for leaky pipes in the ground. So it's going to be transformative in a wide array of sectors in society.
That's a really good explanation. I'm going to put a little bit of a challenge to you. People said that about artificial intelligence. AI is going to be used in everything. ML is going to be used in everything. How do we take this one step further and unpack the quantum opportunity and what that really means and how that can be applied? I'd love to, maybe, and I'll start with you, Andrew, and then I'll throw it open to anybody on the panel. What does that really look like, and how do people harness or think about that opportunity? Because I do think we're a little bit confused as a group, as a general population that are outside the world of physics. We think about the quantum computer and then accessing it, applying it. What does that really look like? What does that mean for us? Because when I remember the first conversations I had with business leaders about artificial intelligence, and the conversation was, well, I have a chatbot on my website. And I was like, that is not what we're talking about here. It is a bigger opportunity. And you've all just covered the entire planet and all of those things. I'd love to get a little bit deeper and sort of see, can you nut out some things that you see where it's being applied either in your research or your work that we can get really excited about and get concrete.
Okay. So I guess there's a lot in that. Okay. So the first thing is, quantum technologies is a really broad church. It includes quantum computing, and that's the one that many people have heard about if they've heard anything about quantum. But everything from sensing through to imaging through to timekeeping are all quantum technologies. Oh no, turn off my phone. Sorry. Okay, you've just disappeared. Let me get you back. Right. So that's the first thing. Now, the other thing you said, now I've forgotten, sorry.
Oh,
there was something else in the question.
Yeah, so I was...
Oh, AI, yes. Okay, so what is the similarity between AI/machine learning and quantum? Is there a new capability that let us do things we couldn't do before? So with AI and machine learning, it's mostly a software capability. So if you have an application where you've been limited by your ability to go through a large set of data, that's where it's transformational. Well, where quantum technology is going to be transformational, it's often in the hardware space. I've got a sensor, I can't detect you know, a magnetic field smaller than a certain amount. Or, you know, if I'm doing imaging inside the skull, at the moment we need these big scary helmets. It's very frightening for children, etc. And with quantum technologies, it's likely we're going to end up with something that will let us see through the skull into the brain, much smaller, much more sensitive, and also friendlier for the child as well. So I guess that's the difference between quantum technologies. It's where you're hardware limited, and something like AI or machine learning, that's where you've been software limited. But in both cases, they're providing just new capabilities you didn't have before.
So Sean, I might throw over to you because you've done this, you've created a company and you've sold it. Can you unpack a little bit more about the problem that you were trying to solve and why quantum was part of that solution? And sort of, you know, I think that might, if you could tell us a little bit about that story and unpack that, I think that'll really help bring some flavor to what we're really talking about here as well. So
there are certain sorts of problems in life which are amenable to solution or improvement with you know, an imaginary quantum computer, something that hasn't been built yet, but you can imagine what it would be when it was there. And so we set out and we were working with an actual quantum computer, the first one in the world, produced in about 2011, 2012 by D-Wave Systems in Canada. And we got to see the potential of what it could do to solve certain sorts of problems. Now, I suppose it's worth saying up front that you're not going to see, well, I don't think you're going to see in the nearest time, you know, a quantum iPhone or a quantum laptop computer or whatever else. You're not going to use it for word processing or email. There'll be certain sorts of problem which quantum computing technology is very, very suitable for, and a bunch of others which it's absolutely not. And so we said, well, those sorts of problems, there's actually a lot of those problems, even though it's fairly boutique, what these machines in theory can do, there's actually a lot of examples of those problems in the world. So let's get out ahead of the curve here and look at what those problems are and start to come up with solutions based on you know, predicted quantum computing capabilities, and work with what we could see right now, so what we could see in front of us right then and what we could play with. And so when the hardware is ready, we would have applications ready to go for that. And we started out in finance because some of our investors had a you know, financial services background, and so they gave us entree to large corporations in finance, you know, the likes of HSBC and UBS, etc., Macquarie Bank, Commonwealth Bank of Australia, which we built a quantum computing emulator for. And we also looked at life sciences and petrochemicals and a number of other areas. And so what we expect to see now is that there will be a continued focus on applications as the understanding of the potential of the technology increases, deepens and broadens across industry. And so when these machines start to come online properly, which is sort of now-ish, companies and institutions will start to pick these up. If you look at where the maturity of the technology is, you can buy quantum computing services via, you know, Amazon Web Services and the like, you know, with a credit card. Are they really powerful and good? Not so much, not yet. Are they boutique and can solve limited problems? Yeah. Do we expect them to improve over time? Yes, we do. How long will that take? Order of years, you know, not weeks or months. But for the big institutions that make a lot of money out of finance or healthcare or whatever, it's worth the time and the investment now. And in fact, over the last 5 years, to get ready for that race when that technology is you know, really commercially viable.
Awesome. Thank you. That was a really good sort of, it's really good to hear sort of what you've done and the thinking behind it, but also where you've applied it and how it was actually applicable to your investors and people that were close to the business in starting up. I might throw to Andre and Jacqui, and I'll either one of you for first and second. But you know, you're both working in sort of unique fields. I'd love to hear a little bit more about where your research, the application of it, maybe an area that you're particularly excited about, and where you sort of see it having a real benefit to either a problem or people or a population group and a solution being delivered. Because I think it's really good to kind of connect those dots, and I'd love to hear from you. So either one of you, whoever jumps in first.
So Sally-Ann, I'd love to explain one of the technologies that we're working on, which might also connect to the previous problem as well, or the previous question that you put to Andrew and Sean, which is, you know, an example of a quantum technology actually that is pervasive in the world and has a huge impact on all of our lives at the moment, and that's the GPS system. So right now, you know, part of what I work in is building the world's best clocks. And in fact, you know, one of the other hats I wear, I actually have a startup company that's providing those. And our first customer is the Australian Defence Force to support a very important defence technology, which is the Jindalee over the horizon radar. So we're currently supplying clocks to support that, to make all Australians a little bit safer by making a key surveillance technology for Australia that little bit better. On the other hand, we've also got a technology which looks to go to space and put the next generation of clocks, very small clocks, but very high performance, onto satellites. And that actually is the basis by which the current GPS system works at the moment. So that GPS system is essentially operated by the US Air Force with no direct costs, but it's important to recognize that something like $2 trillion per annum of economic activity is supported because of access to GPS. I mean, the Internet of Things, you know, logistics, all sorts of things would fall over if we didn't have access to that GPS. So there's really an opportunity if one can provide a bespoke navigation network, or one that perhaps is not so vulnerable to jamming or to other activities which can essentially make it unavailable. And that's an area in which you know, my company is working in right now, to talk about putting very high performance but small clocks into low Earth orbit, and it's quantum that essentially is enabling us to make the clocks much smaller and higher performance than they are at the moment. So that's an interesting, I guess, example of how quantum technology could actually make everybody's lives a lot better.
And it's close. It's coming to market. So you're working on it actively now, which is really exciting to hear. Jacqui, what about you?
So I work with photons. So like, think of laser beams, but particles of the laser beam, so photons. For quantum communications, photons are the best platform because it's the quantum system that can fly from one station to another. And in fact, when we had the intercontinental quantum communication 3 years ago, that was using photons. So I'm just excited by the rate that the technology is actually improving these days. My work personally is, how do you exploit all the properties of that photon? Because when we think of quantum information, we think of the qubit, which is the superposition of your 0 and 1, but actually a photon allows you to do much more. Like, if you think of just the color, you have so many colors. If you think of the shape, you've got so many shapes, like what I showed earlier, right? So you actually have at your disposal a quantum alphabet to encode that information. So how do you use that so you can send bigger messages more efficiently? So that's what excites me.
What I love about this is, as I turn to each one of you and you start talking, you are incredibly excited about what you're working on. But I want to pick up on something that you just said then, Jacqui, but also has come through in both an online question now, but also the questions before the event occurred. And that's about the pace of this technology and where it's going. And Sean, you alluded to this as well, is that we are, you know, the work of building a quantum computer and quantum computers that are readily available is still ongoing. And there's a big piece of work there. And the applications of technologies and the possibility for quantum that you've all talked about, it's still ongoing. You know, I'd love to get from a sense of each one of you of is that pace, are we at that inflection point of up and to the right? This is imminent, it's here now. You know, how do you think about the pace of this evolution? And what is it, if you're a business leader, if you're somebody out there sort of watching this for the first time today and going, what should I be knowing about this? And how do I think about it? And how do I start engaging with it? Because what's now, what's near term, and what's my long-term investment? I'd love to get a sense of all of you from that, because you're obviously very excited and there's things that are launching, but you know, how far away are we really from most businesses in Australia being able to embrace and actually practically engage?
Can I start?
Yeah, please.
So I actually came first time to Australia in 2008 as a visiting student about to start my PhD. And I met then Vikram, who is the Quintessence CEO now. So that was 2008. 2020, so 12 years ago, when I was chatting with him then, like he's got this dream of, launching quantum communication based on continuous variables. When I met him again, maybe 2 years ago, I asked him what's happening, and he hasn't launched the CV quantum communication yet, on the way, but their biggest business is actually securing the information you store in the cloud. So yes, it wasn't the product that they have envisioned, but I think it's changing our lives. Like think of a law firm, for example. You've got all those sensitive documents, and now we store everything on the cloud. What if somebody compromises that location? So now, even if somebody does that, your data, it's encrypted by a quantum random number generator. So it's a byproduct of dreaming for that quantum communication technology. So I think it's affecting our lives now, in the sense that you can find things that you can scaffold with a quantum technology that can make your information, your communication more secure than it is without the quantum element.
Awesome. I'm going to throw open to the rest of the panel for comments. Yeah, Andrew?
So one place to start looking is most countries, and indeed Europe as a whole, have published roadmaps showing where they think the road ahead is going, what sectors it will impact, and that may be a good place for people to start. And they're generally not written for a specialist audience. They're meant to be influencing and helping people decide who are not engineers or scientists. So the Australian roadmap was launched in May this year by CSIRO, and you can find that. But every country now has one. Canada has a national roadmap. I was on a panel call last night with where the representative from Russia was there, and they've decided there's 4 main applications, and they've given it to 4 large state-owned enterprises to run each application. So the railways are now running the clocks, for example.
Wow.
That's a very different approach to what we're doing here, but it'll give you an idea of how seriously people are taking it and where they see the impact.
Sean, did you want to?
Yeah, I think we are at at or near an inflection point. If you look at other technologies, I've been looking at electric power in the last 10 years or so, and I've got a great slide deck which shows from a particular street in New York in 1903. From a particular place, it takes a photo of the street, and it's horse-drawn carriages and a couple of motor vehicles, I think 2 or 3. And 10 years later, in 2013, there's a photo taken from exactly the same place. I suspect it's a set of stairs or what have you. And there are no horse-drawn vehicles on that street. It's all motor vehicles. These things happen slowly. There are some early adopters. In Australia, there's been Commonwealth Bank at the commercial level. There's been some other organisations do it. CBA is probably the most prominent one. And then a handful of years later, there'll be a bunch of others doing it. I rather suspect there's a lot of institutions that are doing it behind closed doors and getting ready so that when it does, because it's real enough now. And that within 10 years, we're going to see a great number of these applications, not broadly across society, probably the high value early ones in finance and medical science. And there are certain problems which are really amenable to quantum solutions, where we can do things literally millions of times faster for very defined problems, and we can get very, very different, better results out of that than we can possibly do today. Then we're going to see, once that's starting to bed down, then we will see, what we saw as a second class of problems emerge, where they're not really even considered problems today because there's no practical way to even approach them with conventional computing technology. And when you start to see the power of the quantum computing technology, people will start to apply those to those problems. They'll become defined as problems, people will solve them, and life is going to change. That's probably 10 to 15 years away, perhaps. I mean, maybe sooner if it accelerates quickly. But I do think we're on the cusp. If you're an early adopter, if you're a large institution or some sort of business or organization that depends on data and analytics and rapid solution finding or large scale solution finding, you'd want to be looking at this stuff now, or else you're going to get caught on the back foot in a few years' time.
Andre?
And I'd just like to add to what all of these other fantastic panelists have said by re-emphasizing that the quantum world is actually a very broad church. And you know, there are things such as the quantum sensing space where there are already examples out there. And so if one's looking to develop a new product in that area, then the market is perhaps a lot more accepting because they can already see the value of those products. And so an evolution in that space. People are thinking that they're probably the first cab off the rank, the developments in quantum sensing. The quantum comms and quantum imaging are coming along a little later, and the quantum computing afterwards. But I guess if the value of exploitation of quantum principles is demonstrated by some of these early technologies that are in less frightening areas, then I can see that, you know, these things are mutually reinforcing as we go down the path.
This is just great. I know that there's a lot of people getting a lot out of this on the conversation and just learning and hearing from all of you from your perspectives. I want to throw this to sort of a national level around Australia, because it's been talked about that Australia's got great strengths in quantum. I think some people maybe know that we do, some people maybe know that we don't, or what areas. But I'd love to hear from all of you. And there's a question that's come up on the chat about opportunities for people in quantum. So maybe could I throw it over to you of what do you think our strengths are specifically in quantum in Australia, where the opportunity maybe lies for us to leverage and for people to engage and look for opportunities either through their business, through their startup, or even employment. And Andrew, I might throw to you. Thanks.
I guess the strengths in Australia at the moment is we've been doing this new quantum technology for a long time. A lot of it began here 20 years ago. So our chief export so far around the world has been people. If you look at some of the leading companies internationally, they're either started or founded by Australians or led by Australians. So the effort in IBM, for example, is led by a student from Griffith University in Brisbane, Jay Gambetta. What Australia has not been great at traditionally, and I think our public institutions need to get much better at that, is that translation and commercialization step. So people like Andre being a professor at the university and having a startup, that should be the norm, not the exception. So if you go talk to people and ask them questions in Australia, they really know the science very well. We are perhaps less well set up than, say, the US or Europe for the translation into immediate impact. But there have been people reaching out. So Commonwealth Bank, Sean mentioned, Sean set up and sold his company. So that's definitely happening. It's just not happening fast enough.
Does anybody else want to chime in on that? Other areas of strength? We've obviously got talent. So what do we need to plug the gap as well?
Look, I might sort of back up what Andrew said, in that we do have strength in the R part of R&D in this case, and some of the world's early leaders, and today continue to be Australians either working in Australia or overseas. Professor Michelle Simmons, for example, very well known in the field. Whether we can then translate that through to some sort of sustainable economic advantage as a nation, remains to be seen. The track record there is a little patchy. I rather suspect that a lot of these organisations will have foreign money come in as time goes by. Certainly we did. Maybe there'll be a change in the national mood, but in terms of whether we're able to do it technically, I think absolutely. Can we find the applications? Absolutely. Can we find people that'll back it and be patient with the inevitable sort of missteps and dead ends and what have you, which happens with new technology? We'll wait to be seen. There are new investors, like Blackbird Ventures out of the fellows that did, Atlassian, etc. They're starting to change the scene and change the mood. And when you get lead investors like that come into something, people tend to pile in behind because they think they must know something. So I'm reasonably hopeful that things will happen, but there's a long sort of way, to go. In terms of, the national strengths, there are a number of organisations now: University of Sydney, University of New South Wales, University of Adelaide. There are others around. The University of Melbourne's got a pretty good effort going. There is Australian National University's got quite a different technology, which is room temperature quantum using diamonds, and they have a company called Quantum Brilliance, and they've actually got contract with the Pawsey Centre to produce operational quantum computing technology for radio astronomy work, and so that's looking pretty promising. but we've still got a long way to go before there are Australian companies selling quantum computers, or more likely, quantum computing services available via the cloud. Is probably the more likely model given what's happening overseas.
Yeah.
So I mean, thanks, Eliane. I'm very much on the hardware side of quantum technology, and so I see that we've got some amazing talent of people that are on the boundary of science and engineering, and that's certainly what I'm crying out for in my with wearing my university hat to fulfill all of the contracts that are coming in through the university, but also what we're crying out for in the company, people that are sort of practical enough to actually manufacture things, but at the same time, you know, have enough scientific knowledge to understand how not to make mistakes when doing those practical things. Yeah. So that's pretty spectacular. I think one, you know, with these amazing efforts that are going around the country, one fear I have is that we really need access to patient capital, because if you're going to play in the hardware space, the payoff can be long. And second of all, you need a much higher investment up front in order to produce the actual devices, the widgets that you need, those first articles. And so that's a real challenge for us as a country, I think, developing that type of investment. And, you know, Main Sequence Ventures is doing it, but, you know, there's not a lot of it. And so I think that's an area that we really could potentially look to as a country to think about where we sort of, you know, take advantage of our intrinsic benefits.
I think that's a really great point. And when I think about investment, and there's a question that I see that's come up on the Q&A that touches into this, you know, somebody was asking about, can equity investments now expect great exits within the next 7 to 10 years? And, you know, I think with quantum, when we're talking about hardware, the reality is if we're starting at that early stage, the answer is no. It's going to be a lot longer than 7 to 10 years. And actually Wi-Fi took 40, you know, and CPAP and ResMed and lots of these other companies that, you know, have a hardware component to them took a very, very long time. You know, we're talking 30 years in that commercialization journey. But I think, you know, Andrew, you and I were discussing this a little while ago. Australia, the government has actually made this investment in the research capacity of quantum for a number of years with this long-term view. And so really what it is, it's not about our investors getting a return quickly. It's about them seeing that the return and the payoff over time can be greater, particularly for the hardware components and what that opportunity lies. And so maybe there's some thinking and some work and advocacy that we can do together about how do we take people on that journey. Andre, just for your company, I mean, you are talking about hardware and clocks in spaces as I've taken it away. So you've captured my brain with one part of your story there, and that's stuck there. But you know, what's the sort of really realistic time frame on that development piece? If we're talking about research, let's just unpack this for everybody that's watching live. You know, what is that time frame from taking it from that idea in the lab to actually seeing that, you know, launch and go live? What's that time frame look like roughly?
My company is really developing a pipeline of different technologies, and so we're taking things out of the university at that, you know, in this technological sort of maturity language, the TRL, like TRL 3 to 4 is where we're taking them out of the university. Because one other aspect which I think is important is that if you're going to actually sell hardware into the market, the challenge is that you need, you know, the service department, you know, any buyer needs to know you're going to still be around in 10 years. And so there's a whole commercial maturity piece that needs to happen within your company in order to assure a customer that you're actually going to be there to fix it when it breaks. And so that's actually a much more challenging problem in some ways than the maturity of the technology. But anyway, to answer your direct question, you know, we're building products that will be in the market within, you know, we've got a contract to supply products within 2 years on the clock piece in order to supply the radar opportunity. But certainly we're on a 5-year timescale to launch our first clock in space, which is, you know, I mean, the device is working in the lab. It's a matter of miniaturizing. And I guess this calls into question another aspect that maybe that we could do in Australia, which is access to infrastructure for small to medium enterprises. How do we access, as a small, wearing my hat as an owner of an SME, is how do we access very high cost diagnostic and assembly equipment, and the challenges around that? Because if we are all individually building that technology, like that allows us to assemble these machines of the future, it's going to be very, very expensive. So if there was a way of collectively accessing these, I think it'd be wonderful.
Some shared infrastructure, perhaps.
Yep. Looks like you've got a little bit, from the macro infrastructure behind you,
Yeah. Sorry, Jacqui, did you want to?
That's a very good point that Andre said, actually, because of just the time scale that quantum technology works, you have to make sure that the market is there when you are ready. And who can predict the future markets, right? That's a problem itself. So yeah, I don't know.
Yeah,
it's one of the challenges.
That's the eternal challenge, right? With startup founders, where they come to you and have this very cool piece of technology, and they go, look what I've done. It's amazing. And I'm going, great. What problem does it solve? And
yeah, like you have to make sure there is a market for it, right? You can't say we'll create the market for it. Like
start with the problem.
Start with the market.
Andrew, you wanted to add something?
So to follow up on Jacqui's point there, I'm really encouraging our colleagues in the universities to go out and talk to non-traditional fields for us. Go talk to someone in agriculture, go talk to someone in mining, and ask them, what problems do you have? Yeah. And I don't mean go talk to an academic in those fields. I mean, go find your local companies and ask them, what's your problem at the moment? What's your biggest fear? What's your biggest risk? Now, a lot of the time, we're not going to be able to help. But sometimes you'll have that conversation and go, oh, we've got something that will do that. And particularly for the quantum technologies on the way, we're inventing a lot of new tools, diagnostic tools like Andre was talking about, etc., to solve problems for ourselves that turn out to be incredibly useful in some other application space that we don't think about because that's not our gig.
Yeah.
So,
and Sean,
well, as physicists, we do things because we can, and that itself is fun. But for quantum technology to move forward, I think that has to change a bit. Like, we should do things that we can do and also responds to some need that society cares about, right?
And we kind of come full circle to Sean, to your experience where you actually had investors, in finance and things like that going, we want this. So talk us through that problem identification piece, because I think that's a really, really valuable piece for all of us to take away here, is starting with that problem. Physicists, you can go out and find solutions. That is the fun for you, wrestling with something really hard. But talk us about that problem identification piece, because I think that's where you started from what I can glean from your story.
Yeah, it is. No, we as a company, our larger company, actually, its business is essentially in sort of problem identification and concept design, a little ba bit of delivery. In fact, Andre, your Jindalee radar work, we do a bunch of the systems engineering for the Jindalee radar, but we've worked on a lot of projects, military, civil, transportation, etc. right at the start, and that always starts with what problem are we trying to solve, not what are we going to build, but what problem we're trying to solve. And when we looked at this as an opportunity, we said, well, what technology? What can this technology, if it evolves properly, what can it do? And we looked at various fields. We looked at medical science. We looked at finance. We looked at infrastructure. What else? Several others. And we said, well, we're a small company, and we spun off a separate startup, or a spin out, if you like, out of Shoal. And it had limited funds and limited people. And you can't go and say, we're going to chase 5 different market sectors, 5 different market verticals all at once. So let's pick one and try and make that work a bit, and then see what we can do elsewhere, depending, and just sort of let nature take its course to some extent. You've got to drive it a bit. And we picked finance for 2 reasons. One is that there are problems in finance which are very amenable to this sort of technology, in theory at least. Things like foreign exchange, pair trading, etc. And that if you can improve that even by only a few %, you've got a very significant advantage in the markets. And we did that, in fact, for an international bank, which was good. And they're also the sort of institutions that have the money to be able to then pay you to do that sort of work. Because if you can show them the return, they'll sort of make the investment. Whereas if you go to things like, you know, medical science and whatever, you know, it's probably more worthy in human terms of you know, improving life for, you know, people on the planet, but the timescales are just so much longer, and you face things like regulatory approval and whatever. And we said, look, that's a later problem. Let's pick something where we can get the quick wins in. And of course, we also had our early investors were from the finance sector, from the likes of, you know, Macquarie Bank, UBS, you know, et cetera. And so that gave us entree to the, you know, the CTOs and the CIOs of these major institutions. And so that worked, you know, that worked pretty well. And so I think, you know, we can find these problems to solve, and we can demonstrate to people that whether it's quantum computing, quantum sensing, quantum navigation, that there really are problems out there where the technologies are amenable, and make those cases. And if you can do it with a little bit of money up front and just do a little bit of risk reduction and show that look, if you invest a bit with us now, we can demonstrate a pathway to success later. And then those pathways, you gradually move down the pathways based on milestones and success. And you're not always going to be successful, but you've got to be a bit realistic about that. But then encourage various investors, and those investors might be, for example, you know, quantum positioning might be the Navy with its new submarines. Now they're not making an investment with a financial return, but there's a lot of, you talk for an hour on this. There's a lot of benefits for the Navy being able to use submarine navigation that, you know, is based on quantum technology and not external factors. Yeah. And so you can find these, but you know, to pick up on Andrew's point, academia, where a lot of the work's done and comes up with the basic physics and takes us up to about TRL 3, 4, 5, those researchers need to get out into the big wide world and actually talk to the people that have the problems and understand the nature of those problems and the details on what's going to make a success or a failure.
I love it. I'm conscious of time, and we've got sort of, you know, this limited window of this brains trust around the table, so to speak, around the Zoom room. I'd love to get to some questions from the audience on here, and there's a great one on here which I see, Andrew, you've put up your hand to answer, and I think it's about capacity. And earlier you talked about Australia being a great exporter of talent overseas, but turns out we're being a really good importer lately too. If John Martinez, who was at Google in the area that I was there, has recently moved to Sydney to join Michelle Simmons' startup, and if it's in Sydney. So, Andrew, what does that signal, and what does that say to the world about?
So, I mean, we export people, but we also import brilliant people from around the world. John Martinez is a really interesting case. He's actually on a 6-month sabbatical from his university, and at the end of that time, he'll go back to the university. And something that works very well in the US and Germany is they have this seamless moving of people between academia, between the government labs, between industry. It's accepted that that's a normal thing and a really valuable thing. I think structurally that's quite a bit harder to happen in Australia. It can happen through the universities, but for example, getting a really good person out of CSIRO is impossible. There's just these structural barriers in place that make it really hard to move people back and forth. Or it used to be impossible. Maybe it's not anymore. I'm thinking of an experience 15, 20 years ago. So what I'd really like at that institutional level is to remove those barriers and let the people move around. You know, I was in retail for 4 years. I'd happily go back and work in a company again. But, you know, doing that in such a way that makes my university happy, that's something that at the moment is negotiated each time on an individual basis. And that takes a lot of time. And we really need to set it up as a normal way of moving people back and forth, because it's the people that make the difference.
And I see, you know, from if I tie together those comments with the previous conversation, is once you're actually in industry, you have a really unique perception about what the problems really are. And a different way of thinking about the solutions that may be out there in market. And I find myself in that space all the time of just connecting the two dots together and kind of going, come together and have a conversation, because really each of you has one of you has a solution, one of you has a problem, and I need you to get into the same room and talk together. So does anybody else have thoughts on that comment about reducing structural barriers and how we might actually break down the silo between research and, you know, I guess industry/startups, because I think it's a really important one that we need to do. I mean, Andre, you're doing it right now. I imagine it's challenging.
So, well, I'm doing it personally, but, you know, I also lead this amazing organization, the Institute for Photonics and Advanced Sensing, where we are working with 50 companies where we're talking to them and solving real world problems. So, you know, more than half of our income every year is now coming from industry engagements rather than from government grants, which is quite anomalous in that sort of physical sciences space that you'd be that engaged. And I must say that this has sort of benefits all around, right? I mean, they're a fantastic client industry if you're capable of delivering, you know, on budget and on time, right? Because you actually put a smile on somebody's face. It's quite a different relationship than the client you have with the federal government if you're allocated fundamental science money for curiosity-driven research. So through examples, many examples in this institute, we're seeing that young people coming in are finding a different type of career within this institute where they're essentially got a stable career where they're working closely with industry because, you know, basically it's a win-win for both the researcher, but also for the industry that's benefiting from that experience. But equally, I'm seeing you know, an additional rigor that's going on even in the fundamental curiosity-driven research because asking important questions, knowing what's valuable is equally beneficial if you're doing fundamental science research. And so there's potentially a new way of doing business for research only people within universities where they are much more outward focused and it could really be beneficial for all.
I think the university has a role to play as well because at least when I started my PhD, it's like the expectation is you will remain as a researcher in academia. You find yourself an academic position and you do the what interests you. It's almost as if you have a PhD and you go to industry, it's like you're a failure. And what I am happy about these days is that I think that culture is changing. It's like we have more pathways for our PhD graduates. And that's really important because we've got to have these critical thinkers, these problem solvers out there in the world, not just in academia. So we've got to have infrastructure for that to happen.
Yeah.
I mean, the on-prime, CSIRO's on-prime really drove a cultural change across the Australian tertiary sector, in my view. You know, it's been transformational about some of the change. You know, as Andrew said, you know, it's common if you're at Stanford and a professor and don't have a startup, there's something wrong with you. You know, and how great it would be if that was the case here too.
Yeah,
we need. I might, you know, to pick up Andrew's point before of identifying a government, academia, industry. I think over the last decade or so, industry and academia have started to work together, you know, reasonably well in places. And you do get people moving back and forth. It's not uncommon now to find people with, you know, good PhDs for practical things in industry. We've got a head of machine learning who's got a PhD in, funnily enough, artificial intelligence, and a couple of other examples. Probably the one leg of the triangle that's probably not working so well is the mobility in and out of government to either academia or industry. It's a bit of an impermeable sort of membrane in both, from both perspectives, which is different to the US. And one of the issues there, of course, is government or the public sector informs policy, and if they're not really well informed, they're not going to inform particularly good policy. And so certainly I'd like to see a lot more movement back to in a way that people can move in and out of government to either academia or industry and really take those experiences and skills. Because a lot of the work our company does is government facing, and sometimes you get some pretty sophisticated people in government that understand how industry works sometimes, but it's the exception rather than the rule. And in terms of risk as well, government tends to be risk averse, and to take a technology out of university laboratories and then make something of it in industry where it earns a return and etc., it inherently involves risk. If you don't like risk, you shouldn't be in this business. And so having a, you know, understanding an intelligent approach to risk management and risk taking is really important, and I think government's lagging a little behind there.
Yeah, look, I think those are all very, very astute observations. And, you know, if I can add one reflection to it, I think the more that we can get people actually outside of the bubble of be it industry or academia or government, the more that we can get them crossing over and spending time in other worlds, it not only expands their own individual thinking and capabilities and skill sets, but they bring something into that organization that they join, even if it is only for a short period. And so breaking down as many structural barriers between things as possible, I think is a really valuable way that we actually get knowledge sharing, we get a greater network and a greater connectivity, and that's actually usually where the opportunities are identified. We are getting really close to time, so I've got one final question for everybody here before we wrap up, and I'm going to ask you to gaze into your crystal ball. And I'm going to ask you, what is the thing that you're most excited about to see in 10 years' time? If you look forward and say, this is what's been achieved in quantum, and I'm just going to leave it very, very broadly. What's the thing that you're going to be so excited about, and the headline that you're going to look forward to see that we're all going to be excited about? Sean, you get to go first.
All right. For me, it's going to be something in life sciences, that quantum technology, computing or sensing or whatever, is going to result in breakthroughs in the life sciences that improves the quality of life of people on the planet. It's nice for people to make money out of finance and to do drive faster cars or whatever it's going to be, but that's really secondary to quality of life and health for the human population. And there are things like solutions to cancer and other cancers and other medical challenges that I think quantum technologies will have a significant role to play in, and I think they will play that role within about 10 years.
Awesome. Jacqui?
I am very optimistic that in 10 years, that is a tight time for our hardware to reach 100% fidelity. But I think 10 years is enough room for creativity that scientists and, us in general can find problems that our noisy intermediate quantum computers right now can really tackle and make a big difference in. So maybe find problems that we can attack now.
Awesome. Yes, I'd like that. That'd be great. Andre?
Well, I guess I'm with Sean in imagining that improving people's lives is the ultimate thing that we really want to do. And so I think that there's realistic hope that on 10 years we could think to have medical diagnostic, medical imaging tools, or things like breath analysis enabled by high performance spectroscopy that can essentially diagnose disease in a non-invasive way and definitely answer that. But because I definitely want clocks in space, Sean's taken that option from me. So let's say that what I'd love to see is an Australian GPS, so we've got our own GPS that gives us much higher performance, so that we can release the autonomous vehicles and things in this country because of the very high performance GPS that we have available to us. I'd love for me to play a role in that as well.
I would love that too, because we were, Google Maps started here with a startup. So why can't we have every bit of mapping and GPS and navigation technology founded in Australia?
Perfect. I'm with you.
Andrew, crystal ball, what you want to see?
The thing I'm excited about 10 years from now is that there will be an application that none of us saw coming. And I don't know what it is. And it's a bit like transistors. When they first came out, the first big market was not radios, it was not computers, it was hearing aids. And no one saw it coming, and that's the thing that drove the technology. And there's going to be something like that for one of these early quantum technologies. It might be measuring vitamin content in juice, I don't know. But there's something coming down the pike where 10 years from now, we're going to go, that was great, and none of us saw it coming.
I absolutely love that. And you know where it's probably going to come from? It's going to be the student that studied in another discipline, or somebody with a completely different background that has a real problem to solve, that walks into a bar with a quantum physicist and sits down and has a conversation and talks about what they're doing and goes, oh, do you think that would work for this? Do you think you might be able to help me solve this problem? And, I think that kind of comes full circle into the conversation today, is that we have incredible capability. We have incredible talent. in quantum in Australia. And we also, as a community, both locally, nationally and globally, we have massive challenges and problems that need to be solved. And if we can come together collectively as a group and as a community and close the gap between those problems and those solutions, those scientists, those engineers, those physicists, the people that can, you know, talk about entanglement and all the other, you know, things that leave the most of us behind when they get into those scientific discussions. But if we can close the loop between those two, that's actually an incredible opportunity to bring solutions to market, but also to create, you know, economic opportunity for lots of people in Australia as well, which I think we can all say we'd be really excited to see. So we are at time. I do want to thank each and every one of my panelists today, Jacqui, Sean, Andre, and Andrew. It's been a fantastic kickoff conversation about quantum and what the opportunity is for Australia. Andrew and EQUUS, thank you so much for partnering with us on this. We're actually really excited about the journey. I think there's a lot of learning to come. And I think that's one of the things for me that I'm most excited about this opportunity, is that I get to come along and to hear from all of you and to learn from all of you, but actually there's a whole community of people that get to learn live with us now, but also, you know, when we share this recording later, there's a lot of people that are going to get to learn and connect with each one of you in the opportunities that we can take forward in solving these problems. So thank you so much for joining us, and thank you for participating and giving up your time and your wisdom and your expertise. I know everybody's going to be hitting you up on Twitter and LinkedIn to follow you and connect with you, and we definitely want to make that happen. For everybody that was watching today, thank you so much for joining us. Please stay involved with us. If you head on over to our website, cicadainnovations.com, you can sign up for our newsletter, and we will keep you posted on all of the events coming up. We will keep you posted with our next webinar with EQUUS, which will be on quantum, which I think is going to be in the new year, because we do want to dig deeper, and we want to go on a journey and unpack that and unfold that for you. So thank you so much for today, for joining us. Thank you, everybody. Stay in touch, stay connected. It's awesome to have you as part of our community. Bye for now.